Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 16. In this lecture, we'll discuss the superposition of waves. This topic is covered in Chapter 18 of our textbook by Surway and Jouet. In this and the next few lectures, we want to consider what happens when two or more waves are present simultaneously in the same medium. For example, consider two people speaking at the same time. In that situation, we have two sound waves that are propagating through the same medium at the same time. We want to understand what happens when these two waves are combined. As another example, consider two people holding the opposite ends of the same piece of rope. Suppose each person is moving his hand up and down, generating waves along the same rope. At some point, near the middle of the rope, these two waves will meet, they will interact, and we want to know how to precisely describe the interaction of two waves that are simultaneously present in a medium. This combining of two or more waves is referred to as the superposition of waves. Superposition is going to be the topic of this lecture and the next few lectures. To give you a glimpse of what could happen when two waves meet, or when they interact, or when they quote-unquote collide, consider the animation here. In this animation, we have two pulse waves. These are not simple waves. These are not the sinusoidal waves we've been studying, but they are waves nonetheless. They might resemble tsunami waves that are generated when there is an underwater earthquake. In this particular animation, we have one wave with a large amplitude with a maximum displacement of 2 propagating to the right, and a smaller pulse wave with a maximum amplitude of 1 propagating left. As you can see, when they combine, they give us a much bigger wave, but eventually the two waves essentially pass right through each other. So waves don't really reflect or bounce off of one another in the same way that particles collide. They seem to simply pass through each other, and when they do combine, the maximum displacements simply add up. So if one wave has a maximum displacement of 2 and the other one has a maximum displacement of 1, when they meet in the middle of the screen, we get a single wave with a maximum displacement of 3. This is a type of interaction that we want to describe in a mathematically precise manner. More generally, when two waves, y1 and y2, interact, the result is a third wave, which is simply the sum of the two waves. So here we're imagining two one-dimensional waves, although this also applies to two-dimensional and three-dimensional waves. For simplicity, we'll consider one wave, which we'll label as y1. That wave is a function of position and time. And then we'll consider a second wave, y2, which also depends on position and time. And when these two waves interact, when they meet or collide or coincide, the result is simply the sum of those two. The sum itself is also a wave. This is a consequence of the superposition principle, which states that the sum of two waves is also a wave. A little more precisely, the superposition principle states that if two functions satisfy the wave equation, then their sum also satisfies the wave equation. Recall that this is the wave equation. It's the second-order partial differential equation. And we say that a function y satisfies this equation when we can substitute it into the left side and into the right side and find that those two sides are equal to each other. If a function y1 satisfies this equation and a function y2 satisfies this equation, then we are guaranteed that the sum of those two functions also satisfies this equation, and therefore the sum is also a wave. The superposition principle basically gives us an easy way to analyze the interaction of two or more waves. If we want to understand what happens when two waves coincide, then we simply add them together and analyze the properties of the sum of those two waves. The superposition principle can be applied to 2 or 3 or 4 or as many waves as you want. However, in this class, we will limit ourselves to the superposition of only 2 waves. The superposition principle can also be applied to waves of any form. However, we will limit ourselves to simple waves, waves that have a sinusoidal form or are described by sinusoidal functions. We will consider 4 examples of increasing complexity in this lecture, and then in subsequent lectures we'll return to these examples and analyze them in more detail. Let's begin with a simple example. Consider the superposition of 2 sinusoidal waves of equal wavelength, equal frequency, equal phase constant, but different amplitudes propagating in the same direction. So imagine you have 2 waves. These could be, for example, sound waves, or they could be water waves in the same medium. These 2 waves coincide. They are present at the same time and in the same place. I'm representing the first wave by this function here, and the second wave by this function here. Notice that each wave is a simple wave. It's described by a sine function. And notice that the 2 waves are basically identical. They have the same wave number, they have the same angular frequency, the same phase constant, and both are propagating in the positive x direction. The only difference between these 2 waves are the amplitudes, A1 and A2. According to the superposition principle, when we combine these 2 waves, we get a third wave. Here we're denoting that third wave simply as y, a function of x and t. We want to explore the properties of this new wave, the combination of these 2 waves. We can see its properties quite simply by factoring out the sine function. We can write this superposition simply as a1 plus a2 times sine of kx minus omega t plus phi. Writing the superposition in this form, we can see that combining these 2 waves, so the superposition of these 2 waves, is simply a new sinusoidal wave whose amplitude is bigger than the individual amplitudes. A little more precisely, the amplitude of the resultant wave, or the superposition wave, or the combined wave, is simply a1 plus a2, the sum of the amplitudes of the individual waves. On the previous slide, we presented an algebraic description of the superposition of 2 waves, but it's also useful to see a graphical representation. What we have here is 2 waves, the green wave and the blue wave, combining to give us the red wave. So imagine that 2 people are speaking simultaneously. One person is generating the green waves shown here, and the other person is generating the blue waves. If you're listening to the sounds that these 2 individuals are making simultaneously, what you would actually hear is the red wave. The red wave is the superposition of the blue and the green. The red wave is also described as the resultant of these 2 waves. The red wave is simply the sum of the blue and the green wave. Of course, remember that these are waves. They are propagating through space. They are carrying energy. So you need to imagine all 3 waves actually moving with some speed. Notice that the resultant wave has the same wavelength, same frequency, same phase constant, and the same wave speed as its parents. So if you look at the 3 waves a little more precisely, you'll notice that they all have the same wavelength. So the distance from here to here, which would be the wavelength of the resultant, is the same as the wavelength of the 2 parent waves. That would be the blue and the green waves. Also, as you saw in the animation a few seconds ago, all 3 waves move with the same speed and in the same direction. What's different about the 3 waves is the amplitude. Notice how the amplitude of the red wave is simply equal to the amplitude of the green wave plus the amplitude of the blue wave. The last example of superposition was a relatively simple one. Let's examine a more interesting case. Consider the superposition of 2 sinusoidal waves of equal amplitude, equal wavelength, and equal frequency, but different phase constants propagating in the same direction. So consider two rope waves, for example, or if you want sound waves or water waves. Wave 1 is described by this function here. Wave 2 is described by this function here. Notice that the two functions are virtually identical. They have the same amplitude and the same wave number and the same angular frequency, and both are propagating in the positive x direction, but one has a phase constant phi1, whereas the other has phase constant phi2. It turns out the sum, or the superposition of these two, is also a wave, and that wave is described by this function here. It's not really obvious that the first line is equal to the second line. We have used a trigonometric identity that is sometimes referred to as the merging sinusoidals identity. It turns out quite generally for any alpha and any beta, a sine alpha plus a sine beta is equal to 2a sine of alpha plus beta over 2 times cosine of alpha minus beta over 2. Using this trigonometric identity, you can probably convince yourself that this first line is equal to the second line. When you look at the second line, you recognize a wave. Clearly, we have the typical sinusoidal function here, and we have a wave number, we have an angular frequency, and then we have a constant here which can be thought of as the phase constant of the resultant wave. Everything in front can be considered the amplitude of the resultant wave. Notice that the amplitude is a little more complicated than the individual amplitudes. The amplitude of the resultant is not just 2a, as you might expect. It's 2a times cosine of phi1 minus phi2 over 2. And therefore, the amplitude could be big or it could be small, depending on what cosine of phi1 minus phi2 over 2 is. To really understand the superposition of waves, it's extremely useful to have a graphical representation of superposition. The animation you see here is representing the superposition we described on the previous slide. As you can see from the animation, the resultant wave, which is the red wave, has the same wavelength and frequency and wave speed as its parent waves. The parent waves are the green and the blue waves that are being combined or added to obtain the red wave. Clearly, they have the same wavelengths. You can read that off from this picture here. The wavelength of the green wave would go from here to here. The wavelength of the blue wave might go from here to here. I'm looking at the peak to peak distance, and the wavelength of the red wave would go from here to here. Examining these graphs a little more carefully, you can convince yourself that all three have the same wavelength. They all also have the same speed, as you saw in the animation. They were all moving together. And if they have the same wavelength and the same speed, then they're going to have the same frequency as well, because remember that speed, wavelength, and frequency are all related. What's different about the red wave, of course, is its phase constant. You can see that each wave has a different starting point, so the three waves have different phase constant. Also, they have different amplitudes, but note that the amplitude of the resultant is not simply the amplitude of the green plus the blue. It's a more complicated combination, which we described as 2a cosine of phi1 minus phi2 over 2. Here's our third example of superposition. Consider the superposition of two sinusoidal waves of equal amplitude, equal wavelength, equal frequency, and equal phase constant, but propagating in opposite directions. So we have two waves now that are being combined. They're virtually identical in every respect, except we see a minus sign here and a plus sign here. That difference tells us that one of them is propagating in the positive direction, while the other one is propagating in the negative direction. So this most closely resembles the case of two waves that are about to collide. It turns out these two functions can be combined and written in this form here. Once again, it's not very obvious how you would go from the first line to the second line. We have once again taken advantage of this little known trigonometric identity. For any angle alpha, any angle beta, you can combine or merge the sum of two sinusoidals into the product of two sinusoidal functions. Remember, in this context, a sinusoidal function refers to a sine function or a cosine function. So you can convince yourself that this first line is equal to the second line if you replace everything in the parentheses here by alpha and everything in the parentheses here by beta, and then combining alpha and beta as instructed in this identity here. When you do that, once again, you find a wave. However, this wave is a little different than the waves we've seen so far. Notice that the amplitude of the resultant is now something that depends on time. This is a somewhat unusual situation. Up until now, we've only encountered cases where the amplitude is a constant number. Here, the thing in front of the sine function, the thing that depends on position, is itself something that depends on time. What we have is a wave whose amplitude is actually changing in time. This animation demonstrates the superposition we considered on the previous slide. We have two identical waves, except that one is propagating to the left and the other one is propagating to the right. The sum of the blue and the green waves gives us the red wave. As you can see, the amplitude of the red wave changes as a function of time, and the red wave does not seem to go anywhere. The red wave does not seem to move, and therefore the resultant in this case is sometimes described as a standing wave. In some sense, the motion to the left of one wave and the motion to the right of the other wave are canceling each other out and giving us a wave that stands in place. So the resultant does have energy, however, that energy is stationary, it's not going anywhere. And most importantly, the amplitude of the resultant of the red wave is a function of time. The fourth and last example of superposition that we want to consider is the superposition of two sinusoidal waves of equal amplitude and equal phase constants, but different wavelengths and different frequencies propagating in the same direction. Notice that wave 1 and wave 2 have the same amplitude. They are both propagating to the right or the positive x direction, and they both have the same phase constant, but the wave number or the wavelength of one is different from the other one. Of course, if the wavelengths or wave numbers are different, then the angular frequencies or the periods must also be different. Recall that the angular frequency and wave number are related using this expression here. V, of course, is the wave speed. It's determined by the properties of the medium. These two waves are supposedly propagating in the same medium. They are, for example, both sound waves propagating through air, and therefore wave 1 and wave 2 must have the same speed. If they must have the same speed and they have different wave numbers, then their angular frequencies must also be different. The resultant of these two waves is then this wave here. To go from the first line to the second line, I have once again used the same trigonometric identity that we've seen 3 times now. We have merged two sinusoidals. We have gone from the sum of two sine functions to the product of a sine function and a cosine function. In fact, this trigonometric identity at the bottom is sometimes referred to as the sum to product identity. As you can see, I can clean things up a little bit. For example, phi and phi give me 2 phi, and then I can divide that by 2. And I'm also going to factor out the x and the t, and therefore I arrive at this third line here after some algebraic manipulations. This third line indicates that the combination or the superposition of wave 1 and wave 2 is also a wave, but it's a much more complicated than wave than we have seen up until now. As you can see, we have the usual sine function, which depends on position and time, and it has a phase constant, but we now also have a cosine function that depends on position and time. This particular type of a wave is sometimes described as a beat. The beat that we described algebraically on the previous slide can be shown graphically here by the red resultant wave. Notice that we have a blue wave and a green wave. They have the same amplitude, they move in the same direction with the same speed. However, they have slightly different wavelengths. The peak-to-peak separation for the blue wave is slightly different than the peak-to-peak separation for the green wave. As you can see, the resultant is a very complicated wave that is different in almost every respect from its parent waves. And its amplitude is not at all constant. At some points, the amplitude is quite small, and at other places, the amplitude is big. So what we have is an amplitude that alternatively increases and then decreases in time. This particular behavior is described as a beat pattern, and we will have a lot more to say about it in a later lecture. Let's end this lecture with a summary of everything we've talked about. In general, we're interested in knowing what happens when two or more waves are present at the same time. This combining of waves is referred to as the superposition of waves. In general, you can combine any two types of waves. However, we will limit ourselves to simple waves or sinusoidal waves. A sinusoidal wave is described by 5 essential properties: its amplitude, its wave number, its angular frequency, its phase constant, and finally its direction of propagation. Of course, there are other properties that we can speak of, but those other properties are related to these 5 properties. For example, one may speak of the wavelength of a simple wave, but of course that's just 2 pi over the wave number. One may talk about the period of the wave, but of course that's 2 pi over the angular frequency. One may speak of the wave speed, and of course that's omega over k, which can also be expressed as lambda over t. So a simple sinusoidal wave is described by 5 essential properties, and we want to know what happens when we take 2 of these sinusoidal waves and we combine them. In general, the 2 sinusoidal waves, like the ones shown here, can be different in every respect. They could have different amplitudes, different wave numbers, different angular frequencies, different phase constants, and they could be propagating in different directions. However, for a more systematic understanding of superposition, we have considered 4 specific cases of increasing complexity. This table here summarizes our explorations so far. D stands for different and S stands for the same in this table. In the first example, the wave number and the angular frequency were the same. The direction of propagation was the same for both waves. Both waves had the same phase constant. The difference was in the amplitudes of the 2 waves. In example 2, which is sometimes referred to as the interference example, our 2 waves were the same, or they were identical in every respect. The only difference between them was the phase constant. In example 3, which is sometimes known as a standing wave example, the only difference was in the direction of propagation. Example 4, which was the most complex example, it is sometimes known as beats, and the only difference there was in the wave number and the angular frequency. In our next lecture, we will come back to example 2 and examine the interference of 2 waves in great detail. In a subsequent lecture, we'll talk about the standing waves, and in a lecture after that, we will discuss beats in much more detail. And that is the end of this lecture. Thank you for your attention.